Hello, everybody. It's wonderful to be here. The conference has been a blast so far. But to all the speakers yesterday, you all set the bar way too high. I'm feeling a little bit of pressure right now. Welcome to my talk, Monster Factory, which is about how we used PDG in Diablo IV. My name is Daniel Maendel. I am a senior graphics technical artist on the Diablo IV team at Blizzard. I was originally a generalist and 3D modeler, but I gradually became more technical over the years. I have 10 plus years of experience, and I've worked in indie, mobile, and now AAA. So in this talk, we're going to cover how we created the Malignant Monsters for Diablo IV, Season of the Malignant, our thought process when approaching large-scale productions, and how PDG was incorporated into our workflow. But first, what is PDG? Now, I'm sure a lot of you know this already, but let's go over it anyway. So PDG, or Procedural Dependency Graph, is an architecture in Houdini designed to distribute tasks and manage dependencies to better scale, automate, and analyze content pipelines. That is pulled from the Houdini website, by the way, not my words. PDG works by running processes on work items. Work items are represented by colored dots. They can be created in a variety of different ways, for example, a Python script or an external input like a CSV or files in a folder. It can store attributes that can be manipulated, and they can be combined, separated, filtered, and deleted. We also can visualize finished, cooking, waiting, and errored work items. Like most things in Houdini, PDG network consists of connected nodes. Nodes and work items are cooked from the top down, and we can control cooking based on dependencies, like, for example, wait for all upstream items to finish cooking before continuing. We can also choose how many CPU cores we want to use, so there's a bit of multi-threaded control and capability here. PDG also has many system hooks. In Houdini itself, it's very common for rendering and geometry to be controlled with PDG, but basically all contexts are integratable with PDG. Python, the operating system, so file management stuff, communications like email, source control and databases, and remote application control, so we can control instances of Maya and Houdini as well. Before we dive into PDG, let's get some context before we get into the PDG here. So first, we're going to go over what is Diablo IV, what content we need, how we produce that content, and finally, how we incorporated PDG into our workflow. Firstly, what is Diablo IV? Well, at its core, it's an ARPG. It has a campaign. It's got in-game content, and it will be having expansions. Later this year, we have Vessel of Hatred coming out, and we have several seasons a year. So we need a lot of content, but let's focus on monsters for this talk. At launch, Diablo IV had hundreds of unique monsters, with many more counting variants. Each monster took an entire team and a non-trivial amount of time to create. For seasons, we wanted to have an impactful amount of new monster content, but seasonal timelines are very quick compared to the full game. And new monsters are expensive. They involve the entire character production pipeline. Game designers and engineers have their roles. And on the art side, we have concepting, modeling, texturing, animation, and tech art who handle rigging, skinning, and simulation stuff. These monsters also often require tweaking and iteration, which adds more time to the production cycle. And that being said, we get the most value from our artists making new monsters. Oops. But there's a distinction between new monsters and new monster content. So how do we make new monster content more efficiently? Well, we already have this fantastic library of amazing monsters. So we thought to ourselves, why not use them, but make them look fresh? We start from an existing monster. We use existing animations. We modify abilities and behaviors. We update or change VFX. And finally, we procedurally make a fresh new look, built to be applied to numerous monsters very quickly. So I said we're going to go procedural for the look. But let's go over the pros and cons of doing that. So on the pro side, it's faster than doing it by hand. Fewer mistakes are made because there's less human interaction, human artists touching it and whatnot. And iteration is easier and quicker, and this is important for a quick production cycle. On the con side, we have a high upfront cost to create the procedural system itself, but generally that's reduced for the next time you do it. Various edge cases can make life difficult as well, but again, that's reduced for the next time you do it because you kind of figure out what is wrong and you can account for that. We also get reduced fine control. But if you have a lot of content or a lot of assets that you need to do, it's better to go procedural. But what does going procedural mean from an art production perspective? Well, on the tech art side, we create the procedural system in Houdini. Concept creates a visual target for us, and texturing will create some reusable texture sets. The modeling and skinning and rigging are handled entirely procedurally, so they are entirely eliminated from the production cycle here. And animations, we already have those, so we don't need to do them. So just a note here, tech art will spend the most amount of time on this. The concepting and texturing take a way less time compared to what we need to do. So let's see how we applied this in Diablo IV, Season of the Malignant. So I mentioned this Season of the Malignant a few times, but what is that? It was Diablo IV's first season. It came out in June of 2023, and it featured Malignant Monsters. So here's a promo image for it, and you're going to see that these tentacle things are going to become a theme throughout this presentation. So how do we start? Well, we start from a concept or visual target. Here we see a paint-over piece of concept art, and this is our visual goal. Breaking it down, we have tendrils wrapping around the monsters. These tendrils have variable thicknesses and lengths, and it's got a texture applied to it. Now we need to make the procedural system to generate a look that matches this visual target. So we made an HDA in Houdini, which handles geometry generation, skinning, rigging, material setup. We've also exposed control parameters, and it outputs a processed file. But let's break it down a little bit further. First, we import our source monster mesh. We pose the mesh for better geometry generation. We solidify the mesh using VDBs. We remove cavities, again, for better geometry generation. And now we need to figure out where the tendrils are going to be located. We start by generating a bunch of points. We connect the points, one for each tendril, and then we iterate through each line. We generate the final path, we apply the tendril profile, and then we repeat, and repeat, and repeat, and repeat. We then transfer the skin weights from the original monster to our tendrils. We restore the final pose, or the original pose. We apply some custom vertex color for the shader in-game. And here's what the completed geo looks like. So the network takes around 30 seconds to cook. It's not bad, right? Of course, cooking is not the whole story. We still need to get the source files for the HDA, we need to set up the HDA, and we need to export to the game engine, as well as all logistical steps like file and directory organization. Manually processing a monster can take anywhere from 10 to 40 minutes. So how many monsters do we need to process? Well, in Season of the Malignant, we had over 200 monsters with around 80 unique meshes. Here's an image of a few of the finished monsters. It's not all of them, that's only a few. So if each monster takes 10 minutes, which is a very optimistic number, processing all 80-ish unique monsters would take 13 hours. Now this is a good amount of time, but it's not crazy, right? Well, let's take a step back and see how we work. First, we want to create an environment where feedback is easy to give, easy to receive, and implement. Feedback from the team is very important, and getting the monsters into game ASAP is a requirement. And the game engine is the most accessible way to get feedback. We always get feedback from the final game perspective. We want to view in gameplay with full motion. We also don't want to zoom in too far, so no pixel peeping. And we want to implement feedback at every stage. For procedural systems, we want to make systematic updates. We want to iterate on the procedural system as a whole. We want to weed out big issues and avoid monster fine-tuning. We also want to update the game assets and get feedback. The advantages to making systematic updates are we can make large steps towards the final look, and we can experiment and make mistakes. And most importantly, we can use a fast iterative workflow. And the final step is polish, but only when the systematic changes are locked in. We fine-tune each monster, we find the best seed, tweak parameters, but polish can take time. And the more time you spend on systematic updates, the less time you're going to have to spend on the polish step, which is what we want. So we get and implement feedback, we make systematic updates, and we polish. However, we still can't spend that 13 hours of processing each time we iterate. So how do we get an iterative workflow without wasting too much processing time? I bet you all saw this coming. We use PDG. For Season of the Malignant, we use PDG mainly to analyze engine data and repository assets, manage the directory and file structures, and automate the production workflow. We cut our processing time by more than 98%. But we need details, right? Before we dive into those details, let's do a recap. So what do we have and what do we need to do? Well, we have a library of monsters. We need a list of monsters to process. We don't want to process everything in the game. We need to locate the source Maya files. We need to extract them to a usable format for our HDA. Maya, unfortunately, is not directly compatible. We have an HDA. We need to process the monsters and get the final geo, and we need to get that geo into the final game engine. Before continuing, let's establish some facts about our working environment. We use Maya as our primary DCC application. All models are exported to the game engine through Maya. We have a series of checks in place that make sure things won't break when they get into the engine. We also have an art repo for all of our source files. We use Perforce as our source control, and it's highly organized. Our engine is our source of truth. Engine data is stored as XML files. Monster assets are linked to mesh assets, and mesh assets have paths leading to the Maya source file. So, as you may already sense, this might be a bit confusing. So I built a little guide, which I'll be referring back to. In the last slide, I talked about how the engine data was stored. Well, at the top right here, we have a representation of that data structure. Here we have the monster at the top, which is connected to the mesh, which is connected to the Maya file path. But the first thing we're going to look at here is the monster list. We get the monster list from our designers. Season of the Malignant required over 200 monsters. This monster list had variants. Variants basically means they've got different abilities, so fire, lightning, poison, shadow, but they all use the same mesh. And this list was not immediately usable in our PDG network. We need the mesh asset for the source Maya file path, and we're given a list of monsters, so the top level. So if we look back to our engine guide, the type of asset is at the top there, where the monster is, and we need to get down to that Maya file. So we need a map to continue. In our handy guide, the map sits here. The engine map is essentially a list of monster to mesh asset. From that, we can then get the Maya file path. For Diablo IV, to go from monster to mesh is a bit tricky to do out of engine. So it says GUID ID numbers here. That's not strictly accurate, but it's close enough for this presentation. So GUID numbers link assets together. A database is needed to match files, because of this, file names don't matter. So here we have a graph where we have prefab A, which represents our monster, which is linked to a, it's really unfortunate that we're in a chapel. It's linked to mesh GUID 666. It's a Diablo game, guys, come on. And then the database is then needed to figure out that mesh2.xml, which has the GUID of 666, is that the mesh asset that's linked to it. In Season of the Malignant, the database was inaccessible on short notice. So we needed to make our own database or map. So here's a graph of the PDG network that we used. So PDG is capable of handling massive amounts of data. We scanned every monster and mesh asset in the game, and then they are matched together by their GUID numbers. We scanned over 150,000 files. It took about 10 minutes, and then this network only needed to be run once, unless there are changes to the game files themselves. We saved the output as a CSV file, or map, we like to call it. And we don't need to do it again. Let me just simplify what I just said. So here's our guide of the engine structure. Just going to expand it a little bit, give it some color. So at the top level, we have our monsters. The green ones there are our meshes, and then the blue ones are our Maya files. So we have multiple monsters that are linking to the same mesh, so those are considered variants. But then there are also situations like Monster E where they just have a unique mesh. So in the output CSV file, our map, the monster is represented by a row, and each column is relevant data, such as the monster name, mesh name, and the Maya file path. So the mesh name and the Maya file paths have repeated items, but all the monster names are unique. With the map and the monster list, we can construct our mesh list, which is a list of unique meshes with source files, right? To construct this list, we transfer the appropriate attributes from the map to the monster list, so the mesh name and the Maya file path. We consolidate variants so that each work item will be unique. This helps avoid repeat processing, and it reduces our list of 200 plus monsters down to about 80. We write out a CSV file for our final mesh list, and this list, the CSV, can be manually edited to include HDA parameters, and this is useful for our polish step. After generating and editing this list, we should avoid overwriting it to prevent losing our work. More monsters can be added, however, but that's a little bit more of a manual process. Typically doesn't happen that often, though. So here we have another graph. So at the top here, now our mesh is linked to our Maya file, which is then linked to our monsters. So it's basically flipped around. On the CSV side, each row represents a unique mesh and Maya file. The monster names have been made into a list. Now, this isn't strictly important for the workflow automation, but it is really useful for doing logistical steps later on and for production. We also have a seed column there, which represents our manually created HDA parameter that we can use in the network. Now we have everything we need to automate the workflow. Let's start by pulling the Maya source files from Perforce. With a huge project like Diablo IV, pulling all the source content from the repo is not practical. We need to be more surgical. Fortunately, with our mesh list, we can pull only what we need to, right? We got those attributes. We have the Maya file path. But we also want to pull any dependencies and any references that are needed. We can use the Perforce PDG node or a Python script to do this. And once completed, we have what we need to perform the extraction. So getting a usable file for our HDA. But before we go further, it's important to plan where our generated files are going to live. So these are transitional files. These ones here. So we have our source monster, which is coming out of Maya, our process monster, which is the result of our HDA, and then we need this Maya file for export into the engine. So let's generate these. We use the Maya file path from the engine and the mesh list to construct other paths. We store them as work item attributes, and it's done typically through our Python code. We also create the required directories, and the more organized the project is, the easier this step will be. So you can see here, we have like 80 work items on our PDG network, and so this is getting the source Maya files there and creating the directory structure. Now that we have our source Maya files and destination paths set up, let's perform the monster mesh extraction. So here we use a Maya server setup. This creates a headless Maya instance, and we use the send command node to control that Maya instance and perform the extraction. We output the extracted file to the path we just set up in the last step. And this only needs to be run once, unless there's a change to our Maya source files. Edge cases may require us to do some code adjustments along the way, especially with this operation being run on 80-ish files. Now we pass that extracted monster through the HDA. I talked earlier about systematic changes, and here's where they would be made. Also note that this will be the start of our rapid iteration cycle mentioned earlier. This step will give us the final mesh we need to get into the game. We use the HDA processor PDG node. We configure it by linking our Malignant tendrils HDA and use work item attributes as HDA parameters. So our input files and our output files, file paths, and any custom attributes that we created in that mesh list CSV file. Once processed, we have the final files needed for export into the game engine. Almost there, guys. Our final step is to get those processed monsters into game. So that's representative of this step here. As mentioned before, for Diablo IV, we need to go through Maya. We use a similar method to our extraction step, where we use the Maya server and the send command nodes. But this time, we need to construct a scene. We need to import our output file from our HDA. We need to format the scene. We need to save it, and we need to export. And now we have our assets in the game engine. And we can start gathering that feedback, that juicy feedback. So just a note here, there is a bit of engine work that needs to be done, but it is minor. And there we go. We've gotten our asset into the game engine with an automated workflow. While developing these systems, debugging may be required. To debug a PDG network, failed work items will have logs. We can also trace upstream to track down issues, and we can see all attributes on each node. Also, validation checks can help prevent issues, so checking before a file exists before actually doing anything about it. HDAs can be debugged in Houdini itself, set up manually. We can match the HDA parameters to our PDG network or the CSV file. And on the Maya server side, it often requires testing inside of Maya and recreating the Python code in Maya natively to figure things out and debug. So with our PDG network operational, we can start our quick iteration cycle and make those systematic changes to the HDA. We implement feedback, add or remove features, experiment, optimize, reprocess, export, and gather feedback. Manually, one iteration took 13 hours. With PDG, it takes 10 minutes. Once feedback starts becoming monster-specific, we can start the polishing step. In procedural systems, seeds are not equal. So for Season of the Malignant, we exposed several parameters for fine-tuning. Seeds, tendril controls, and monster source configurations like posing and VDB settings. We use the PDG attributes and the CSV inputs to fine-tune each monster independently and maintain the automation. So our objective here is for the result to look great out of the box, but there is that room for polish if needed. With all monsters processed and polished, we now need to commit our source files. We have around 250 new files all over our folder structure. And gathering all these files would take time and we might miss some. Luckily, with our PDG attributes and a per first node, we can commit all of our generated files procedurally. We can also generate CSV reports for helping with the production and logistics. Producers love that, just so you know. And here we can see a full network that I talked about in this talk. That's the full network. There's no subnodes. It's not that complicated. OK, one final recap. We have produced a ton of new monster content. We've vastly reduced our iteration times, and we've made the monsters feel fresh. And for the future, the workflow has been proven successful. Initial costs have been reduced. HDA and PDG networks can be duplicated and adapted to do different things. And we can try new and crazy things. We are fortunate to be able to make this into a reality. We had great leadership who greenlit this new tech and gave us time to research and develop. We had wonderful teams that helped us. Shout out to our character and pipeline tech art teams. Content creators who made our amazing monsters, so concept, character art, animation, design, and an engine team who enabled us, who made new tech to make it all work in-game. And a special shout out to my colleague Sky Yin, who helped a lot during this production. And that's it. Thank you very much.
Okay, we are ready to take some questions.
Hello, thank you for your talk, really interesting. I was wondering about, since Diablo is such a fast-paced game and players really need to quickly recognize what type the monster is and what they can do, are there things that you do in the scatter step, for instance, that avoid cluttering the silhouette of the monster or something
Absolutely.
like that?
Yep. Yeah, we have various controls that are built into the HDA network that mask out specific areas. I think on this one we tried to avoid the face area because that's a recognizable feature, and we didn't want to have tendrils that were too big to muck up the silhouette of the character, because typically, if you're a concept artist, the first thing that you're taught is the silhouette is the first thing your eye sees, right? So we wanted to maintain that shape so that players would quickly recognize that, oh, that's a goat man brute monster. So yeah, absolutely.
Hello, over here.
Hello.
Super awesome how you broke such a complex topic. I have a question mainly about the HDA that is plugged into the processor. Did the character artists work directly in Houdini, and who was responsible for basically starting a new pipeline, a new set, like this iteration phase? Like, I imagine that they were tweaking it, and at some point they came to you guys and said, okay, run it again on all the monsters, and then you would see it in game. Was that the flow of how it happened?
So we were given a good amount of freedom. The tech art team, so basically myself and my colleague were the ones that did all of the HDA work. We were given that visual target at the beginning, and we're just like, try to hit that. We got some feedback from the team at the early stages, right? So like when I talked about those systematic updates, the art team is involved in those. So we'll make a change, we'll upload the assets, and the art team will be like, that doesn't look good, could you change something like that? So they're involved, but the tech art team, myself and my colleague, were the ones to implement all of the changes to the HDA and do all of the legwork, right? Does that answer your question? Yes. Oh, sorry.
Yeah, thank you. Thank you very much for this talk. Could you elaborate a bit on the, after this generation happened, what was the per monster tweakings that you made, and more specifically, if there was some handwork involved after this process took place?
Yeah, I think the thing that we worked most on was making it look good in motion, the tweaking. The breakdown, we had the monster, like normally it's in like a Y pose, but then you saw that we made it into a T pose, right? So doing tendril generation in like tight areas was a problem because we got a lot of stretching when the animations played, right? Because we're transferring skin weights. We don't have a whole lot of and we don't want to touch the skin weights manually. We don't want to go in and be like, oh, that skin weight doesn't look good. Let's paint it a little bit. We want to avoid that. We want to keep the pipeline entirely procedural. So a lot of our time was spent just making it good out of the box. And for the example of stretching, that was like putting it in a T-pose so we don't get some weird tendrils going from like the upper forearm to like the hip area and then having like a big stretched area. Does that kind of answer your question?
Hi, hello. My question's about exporting from Maya. So Are your artists working to a certain convention or a certain structure in the project that lets your HDA pre-process correctly, or do you have to do some cleanup there? Was that easy or a difficult thing to achieve?
It wasn't the easiest thing in the world. Diablo's been in production for 7 years, so things have changed over that time. So like doing some of our older monsters had like a slightly different file convention, but we didn't have like too much trouble creating the code that basically figures out where things are gonna go. So there's a lot of checks in place that make sure things don't break, essentially. Does that answer your question? Okay.
One last question. No?
With regards to the Perforce integration, and you're touching so many files, some files are new, some files are getting updated, and so some need to be added, some need to be opened for edit.
Yep.
At what point do you know the name of the file, and how do you avoid delays in cooking as a result of computing the file name, because you have to open it to edit before you can write to it?
Yeah. Can I just reverse the slides here for a second? I need an aid for this question. All right. So, let me go back a little bit further. So, in something like this, we have these switches right here. So we can choose which things that we want to process in the PDG network. And a lot of times I won't even use a switch. I'll just like select this node and like cook that one, just to make sure that that situation doesn't happen. So, and I'll have a series of checks in place to make sure that the file is checked out, that it's readable, right? That I can override it, because if I don't, then like you said, it'll run the network, but then nothing will change.
How do you know the file name before you've run the network?
Good organization. Oh, and the engine data, right? Because our engine, the XML file has the Maya file path. It's not always accurate, but we've created, it's like doing a Perforce pull, but with a wildcard. Just give me all files of this type kind of thing. And then I go through and I search each one, even going to the point where I'm opening it up, and like this is all procedural, and like locating the specific, like we have export sets in each file, so locating the specific export set. There's like a whole, like I didn't get into that, so it is more complicated than I set up here. But yeah, we do have that kind of functionality to go in and locate the proper Maya file, if there's more than one, and the proper export set, and yeah.
Okay, thank you very much for that lovely talk.